All
right, so our first section we'll look at is 3.3. Two big things we're going to look at in this section is factoring and how division helps you to factor something. So what I'll do is I'll try to explain the concept with just numbers first, okay, really simple numbers, and then we'll actually do it with polynomials. All right, so just a reminder, we've said this before, but a zero or a root of an equation is a number that you plug into the equation and get 0. Okay, so for example, if I had something like y equals 2x plus 4, the root is negative 2. It's the number that I plug in for x, and I get 0 for y. Okay, and the second way I've written it here, this IFF, that's an abbreviation for if and only if, okay, which is from geometry. It means you can read it forwards and backwards. It means if something is a root, you can plug it into your function and it'll equal 0. Or if you plug a number in and it equals 0, then it's a root. So it's an if-then statement you can read forwards and backwards. Works both ways. All right, so we're going to use long division, okay, with polynomials to find roots. And what long division is really going to allow us to do is factor. And factoring is what finds the roots. All right, so we'll start out with just a basic number, okay, like 12. Okay, first, what does it mean to factor? If I asked you to factor the number 12, what does that mean to do with it?
Yep. Find like the multiplying to it.
Yeah, find two numbers that multiply together to give you 12. Now, if I tell you 3 is a factor of 12, okay, I'm telling you that 3 is a factor. How could you use 3 to find another factor of 12? What could you do?
Divide it into 12.
Yeah. If you know something is a factor and you divide it in, the answer that you get is another factor. All right? So telling you that 3 is a factor means 3 times something gives you 12. And as Nick just said, if you divide each side by 3, 12 divided by 3 gives you 4. Right? So now we know 4 is also a factor. Does anybody know what you call that when you divide two things, the answer that you get? Like when you add two things, it's the sum, or when you subtract, it's the difference. How about when you divide them? Yeah?
A quotient.
The quotient. Exactly. All right, so the key is the way you can figure out if something is a factor. Let's say I asked you, is 5 a factor of 12? Well, if you try to divide 5 into 12, and you look at the remainder, 5 doesn't go into 12. Okay, without a remainder. Because there's a remainder of 2, that means 5 is not a factor. All right? If I said, is 6 a factor of 12? Okay? When you divide 6 into 12, do you get a remainder? No. So that means 6 is a factor, and the quotient is 2. Right? 12 divided by 6 is 2, and 2 is another factor of 12. All right, so the key is if you can figure out something that is a factor, you can divide it in, you won't get a remainder, and the quotient is also a factor. And so we're going to do exactly the same thing, except we're going to do it with polynomials. Right? We're still going to look for all the same things. Look for a remainder of 0, look for that quotient, and we know the quotient is a factor as long as you get a remainder of 0. All right, so that's exactly what I just said to you guys. Okay, if you divide two things, you get a remainder of 0. You know that what you divided by is a factor. Okay, and factoring makes it very easy to find the roots. All right, so if I gave you an equation like, let's say, x squared plus 8x plus 15. And I asked you to solve it. Well, just by looking at it, it's kind of hard to figure out what are the two numbers you plug in for x and get 0. But if you can factor it, like that, x plus 3, x plus 5, then all you have to do is find out what number do you plug in here to make the first one 0, and what number do you plug in here to make the second one 0. Right? If you can't factor it, then you could use quadratic formula. But if you can factor, that's generally the easiest. So the two numbers that you would plug in that would make this one 0 would be what? -3 and -5. Yep. So I'm going to show you how to use that exact same process we just did. Okay, the 12 divided by 3, getting the remainder of 0, and looking at the quotient. I'm going to show you how to do it with a polynomial. I think the easiest way to probably do it is, as I show you each step, in the written out rules, it's probably easier if I just actually do it so you can kind of see how it works. All right, so when you want to divide polynomials, okay, the first thing you have to do is look at your dividend, which is that part. And you've got to make sure you are not missing any terms. Okay, so you look at your highest term, look at that exponent. Okay, in this case, what's my highest exponent? 3. So I got to have every single term from cubed all the way down to my constant. Okay, am I missing a term? Yeah, I'm missing the x squared. Okay, so what I'm going to do is fill in 0x squared. If I don't, what's going to happen is when I start doing this, I'm not going to have a place to put any of the squared terms. Okay, because the goal here is going to be to line things up in columns, okay, like terms. Okay, so we're going to make sure we have a column for each term. Okay, so what I'm going to do is just rewrite it, x cubed, and I'm going to just put plus 0x squared. Okay, and keep everything else the same. Okay, any questions on the first step? All right, second step. You're going to divide the first term of your divisor, which is that, into the first term of the dividend, which is that. Okay, so off to the side, what you're trying to do is x cubed divided by x. Okay, that's what we're doing in our head right now. Okay, so if I do that out, what is x cubed divided by x? Yep, Ian?
X squared.
Yep, x squared. Good. Okay, so we're going to put that answer up there. In this case, it doesn't matter where you put it. Okay, put the x squared anywhere you want. Now what I'm about to do, I need to line things up in columns. Okay, we're going to multiply our answer from step 2 by each term in the divisor. Okay, so basically what we're going to do is multiply this back out to each term. Okay, and make sure you put the result under the correct column. Right, so Hannah, what's x squared times x?
X to the third.
Yep, x to the third, and x squared times -3
Minus 3x.
minus 3x to the
Second.
second. Yep, perfect. Okay, so that's step 3. Just multiply that term back out. Now step 4 is to subtract the columns. Okay, and this is where people usually make a mistake. Okay, so what I want you to do with step 4, put a minus sign and put parentheses around all of that. Okay, so you're subtracting both the x cubed and we're going to subtract the -3x squared. Okay, from what's right above it. All right, so we'll start with this part. Alex, what's x cubed minus x cubed?
would that just be 0?
Yep, that should always happen. Okay, and now the next part is 0x squared minus 3x squared. So Ryan, what would that come out to? So 0x squared minus 3x squared.
It's just 3x squared.
3x squared. Yep. Okay, and now notice what happened. Okay, now I have a squared term. I started with a cubed term. Okay, each time you do this process, this exponent is going to come down smaller, lower and lower. Okay? And what we have to do is keep going until this exponent is less than that exponent. All right? So the bigger the difference between those two terms I circled in red, the more times you have to do the process. Right? So the last step is bring down your next term. Okay, so I'll do that. Some people like to, put an arrow, however you want to do it. So bring down your next term and keep repeating it, either until you don't get a remainder. Okay, if it comes out remainder 0, or the degree of your remainder, which is what I circled in black, is less than the degree of my divisor. Right, so we keep repeating steps 2 through 5. All right, so the next thing we're going to do is divide x into 3x squared. It's off to the side. Just write down what I'm going to do. And Sam, what do you get if you divide x into 3x squared?
3x, 3x, yeah, 3x.
Yeah, just 3x, yep. Okay, now take the answer, whoops, that should say 3. Take the answer that you just got in step 2, multiply it back out, and just make sure you line things up in columns. So Fred, what's 3x times x?
3x times x. 3x squared.
Yep, 3x squared. And how about 3x times negative 3?
Negative 9x.
Perfect. Step 4, I'm going to subtract. Okay, again, make sure you put parentheses around it so you remember you're really distributing that negative out. Okay, Ethan, what's 3x squared minus 3x squared? 0. That's gone. And John, what's negative 8x minus 9x?
Would just be x.
Yep. So that minus a minus turns into a plus. And now I don't have an exponent here that's visible, but Austin, what exponent is really on that x?
1.
It's really a 1. So now the degree of my divisor and the degree of my dividend are the same. Okay, we have to go one more step, and then this is the last step. And then the degree will finally be smaller, the degree of my remainder.
Where did you get 6 to the second minus 9x?
Where did we get 3x to the second from? So when you multiply 3x back out to x, that's 3x to the second.
Okay.
And then 3x times negative 3, that's where the negative 9x comes from.
Okay. Thank you.
Okay, and now bring down my next term. And what am I going to divide into what this time? Brad, you think you could tell me what I'm going to divide into what?
You're going to divide x to the first time.
Yep, x to the first into,
Into x to the first.
yeah. So what's x divided by x?
It's just cancel.
And so what do you get?
So it would just be 1.
1, yes. Divide two things that are the same, you get 1. Now, if all they asked for was the quotient, you're done. That's the quotient when you divide these two things. If they want the remainder, I get to keep going. All right? So let's multiply it back out, see what we get for a remainder. So 1 times x gives me x. 1 times -3 gives me -3. Subtract. And what is my remainder here?
6.
Yep, 6. Sometimes people look at it quickly and they say, oh, +3 -3, it's 0. But remember, it's minus -3. Okay, so my remainder is 6. Okay, so there's 2 ways you can write your answer. You can write quotient, x squared plus 3x plus 1. And the remainder is 6. Okay, that's one way. This way is not as helpful if you want to check your answer. Okay, if you want to write it in a way you can check it, let me show you how you do it with regular long division, and I think you'll see how to do it with this. Let's say I did, let's do 2 divided into 13. What's the quotient when you divide 2 into 13?
0.
2 doesn't go into 13? Wait, did you say 0?
Yeah. 6.
6. Okay, quotient is 6. What's your remainder?
0.5.
Remainder should always be an integer. Should get an integer for the remainder. What is it? 1. Okay, just like 4th grade long division kind of stuff. 2 into 13 goes 6 times with a remainder of 1. So you can write your answer that way, or you can write your answer like this: 6 plus your remainder over your divisor, right? 6. Let me write out what I just did. 6. You know what? Let me write it like this. It's your quotient plus your remainder over your divisor. Okay, so in this case, you could write 6 plus a half or 6 and a half. You could do exactly the same thing with our polynomial. Take your quotient, okay, which is what you got when you divided, x squared plus 3x plus 1, plus your remainder. Remainder was 6 over my divisor. What did I divide by? X minus 3. And the reason I like this way a little better is because I can check that answer. I could type this in on a graphing calculator. I could type in the original problem on the graphing calculator and see if they come out the same. Right, so I'll check this one just to show you, but I'm not going to check any other ones today. All right, so type in the original problem. So you get x cubed minus 8x plus 3. And you're going to divide by x minus 3. Okay, that's just the original problem. Now type in what you think you got for the answer. Okay, and you got to type it in the second way. Let's try that. There we go. All right, so x squared plus 3x plus 1. And just to type that last part in, be careful with parentheses. So I'm going to do plus 6 divided by x minus 3. And I'm going to put x minus 3 in parentheses. All right, so if we did this right, those two things should be identical when we graph them. Okay, this step's not necessary, only if you want to check your answer. Okay, so that's the original problem. And the one in red is the one that we got. Okay, do they look the same? Yep. So that means our answer is correct. Okay, but that's the pattern you can follow. Same things you did in long division. Quotient plus your remainder over your divisor. Okay, so any questions on that? Yeah?
Can I just get a definition of what the quotient and then the divisor
Sure. So the quotient is the answer that you get from a division problem.
Okay.
So in this case, that's my quotient. The remainder, that's the thing you're left with at the end. So that's your remainder. And your divisor, that's the thing that you were dividing into. That's your divisor. The thing under here, that's called the dividend. X cubed minus 8x plus 3. I can label that too. I'm not going to circle that one in blue because that's not part of the final answer. It was part of the original problem. That's your dividend. Okay, so quotient, divisor, dividend, remainder. Yep, good question though. A lot of different terms. Okay, any other questions on that? So if we kind of connect this back to what we said about factors, did x minus 3 go into that evenly? Nope. When I did it, I had a remainder. So does that mean x minus 3 is a factor of that dividend? No, it's not. Okay? If you were trying to factor it, that's not one of the factors you would use. All right. All right, so let's try this one. Okay, this time I already set it up for you with the missing terms. Okay, we were missing the squared term and the linear term. But we had the fourth degree term, we've got the cubic, and we've got the constant. All right, so step one, make sure you're not missing any terms. Okay, we're good. Step two, take the first term of your divisor and divide it into the first term of your dividend. Okay, so Curtis, basically what I'm doing is this. And what is 2x to the fourth divided by 2x squared give me?
X squared.
X squared, good. Okay, multiply that back out to everything. X squared times 2x squared is 2x to the fourth. How about, John, what's x squared times x? X cubed. And Ian, what's x squared times 1? Okay, and what am I doing with all that stuff I just wrote? In one word, what am I doing? Subtracting it. So make sure you do this. Okay, 2x to the fourth minus 2x to the fourth. Negative x cubed minus x cubed. It's like negative 1 minus 1. Okay, it's negative 2. Okay, be careful you don't do negative 1 plus 1. That would be 0. Okay, it's minus. And then 0 minus x squared. All right, and one more thing I got to do before I can start the process again. Bring this down and watch what's going to happen here. Something nice is going to happen here, and I think this is actually going to be our last step. Okay, sometimes what's about to happen does happen, and it's kind of nice. All right, so now we're going to divide negative 2x cubed by 2x squared. Yep, negative x. Okay, multiply it back out. Adrian, what's negative x times 2x squared?
Negative 2x squared. And then negative x squared.
So you got x squared for both of them, but I think the first one should be a different
Oh,
exponent.
I mean x cubed.
There you go. So negative 2x cubed, I agree with the negative x squared.
Yep, and negative x.
Negative x. And we're subtracting. Okay, Nick, what's negative 2x cubed minus 2x cubed?
0.
Yep. And how about negative x squared minus x squared?
0.
Yeah, so what just happened is two things canceled out in the same step. It doesn't always happen, but when it does, it's kind of nice. Yep, what were you going to say, Adrian?
I was going to say.
Nope, nothing. All right, so what do I get for my last step right here?
X.
Just x. What's the exponent on that?
1.
1. What's the exponent on the first term of my divisor?
2.
1 is smaller than 2. I'm done. Okay? You can't divide 2x squared into x. Okay? So now we're done. Just bring this down. And that's my remainder. X minus 2. Okay, so I'll write this one both ways for you. Yeah?
Where did you get that minus x from? That's on top.
The minus x, that comes from doing negative 2x cubed divided by 2x squared.
Oh.
All right, so your quotient, x squared minus x, remainder, x minus 2. Okay, okay to write your answer that way, but not the best. So let's do the quotient plus remainder over divisor. So quotient plus remainder. And what was my divisor here, just to make sure we know what that is?
2x squared plus x plus 1.
Yep, 2x squared plus x plus 1. And now if you're careful, that's something you can type in. You could graph it and see if what I just put in the box and the original problem come out the same. Okay, but I'm not going to check this one. Okay, any questions on that? All right, so we still didn't get a remainder of 0, which means that what we tried to divide into it is not a factor. Okay, that does not go into it without a remainder. Okay, we will do some that actually divide nicely.
What is it, man?
The last one? Or was it a minus on my divisor?
No.
Yeah, it's a plus 1.
Yeah, I see.
All right, so there's different ways of rewriting things. I think the easiest thing to explain this is I'll just show you with the numbers we just used, 13 and 2. Okay, let's say we take 13 and divide by 2. Okay, the quotient that you get when you do that is 6. And the remainder that you get when you do that is 1. Okay, what this formula is giving you is basically a different way to write your numerator. Okay, and it's a way you can check your answer with arithmetic. Okay, a little harder to check your answer with a polynomial, but with arithmetic, this is really fast. I'm just plugging in each of the numbers I just wrote up above, just to show you how this formula works. If you did your division correctly, okay, your numerator, okay, or the thing that's in the top of the fraction, okay, your dividend, should equal what you divided by times what you think the quotient is plus your remainder. Okay, so you might have done that in elementary school to check your answer. Okay. Take your divisor, multiply by your quotient, and add your remainder. If you did it correctly, that should equal the original dividend. If you did it wrong and you get the wrong quotient and the wrong remainder, the left and right won't equal each other. Right, so it's just giving you a way you can check your answer. I think it's easier to check it on the calculator, but this method would work as well. All right, so remember, when you do long division, the way that you know you are done is one of two things happens. Either everything cancels out and your remainder is 0, or the degree of your remainder, that exponent, is smaller than the degree of your divisor. All right, so let's say I had a problem and I divided by a linear polynomial. Okay, I'm just going to make something up. Okay, x plus 5, that's a linear polynomial. It's a line with a slope of 1 and a y-intercept of 5. So if I do this long division, I know the degree of my remainder is going to be a step below linear. What's the exponent on that x in the x plus 5? John? 1. Okay, when you do out the division, the degree of your remainder has to be smaller than that number. So what's smaller than a degree 1? A degree 0. And what's another name for a term that has a degree 0 for the variable? We normally don't call it that. Yeah?
Isn't just 1?
So it's a term I'm thinking of, begins with a C. Constant. Okay? So if you divide by something linear, okay, meaning you divide by something that the highest exponent is a 1, your remainder is just a number, okay, a constant. Okay. If you divide by something like I did here, 2x squared, your remainder is not necessarily a constant. It's going to be a step smaller than x squared, which is x to the first. Okay, but that's not a constant. Okay, so if you divide by something linear, the remainder is a step below linear, which is a constant. Sorry. Right, so what that leads us to, and your book kind of goes through the proof of why this is true, but we're not really going to go through the proof. That's what I just erased. Is this idea leads us to what's called the remainder theorem. If you divide by something linear, and all you want to know is the remainder, there's a quick way to find it without doing division. Okay, it's a really quick way. And why might you want to know the remainder when you divide two things? Why is the remainder really important? What does it tell you? We've kind of talked about it already. When you divide two things, the remainder can tell you something, especially if it's a certain number. Yep?
If you can factor it.
Right. It tells you if what you divided by is a factor. So rather than doing the whole thing out, you can quickly tell if something is a factor just by checking what the remainder is and see if it's 0. Okay. And this is the quick way to check the remainder. Now, unfortunately, the theorem only works if you divide by something linear. Okay? It could be x plus or minus a number. Okay? You can't divide by x squared. You can't do this with x cubed. Okay? It has to just be something simple. Okay? Like the next problem is going to be. I'm going to divide by x minus 3. All right. You know what? I'm going to leave this just as minus. It does work with a plus, but you'll see why I'm going to leave it as minus. Okay? So it's got to be written this way. X minus a number. Okay? And to find out what your remainder is, okay, so you have some function in the top. You're going to divide by x minus c. Okay, if you want to know your remainder, just take that number, okay, whatever comes after the minus sign, and plug it into the top function for x. That's all you have to do. You don't have to do any division. It turns into just plugging in the number after the minus sign in for x in the numerator. Okay, and that'll tell you the remainder. Okay, but keep in mind, whatever comes after the minus sign. All right, so let's do this. And again, we're not going to do out the whole division. We're just going to find the remainder when we divide those two things. Okay, so let's take f of x and divide by h of x. So that's x cubed minus 2x squared plus x minus 5. And I'm going to divide by x minus 3. Okay, what's the number after the minus sign in that one? Oh, Connor? What's the number after the minus sign?
Which one is that?
In our denominator.
Three.
3. Okay, so we are dividing by something that fits the pattern I just explained. Okay, x minus a number. So take the number after the minus sign and plug it in for x in the top. Okay, so I'm going to find f of 3. Okay, just plug 3 into the top and that'll tell you the remainder. 3 cubed minus 2 times 3 squared plus 3 minus 5. What this theorem won't do is give you the quotient. If you want the quotient, you got to do the whole thing out. Okay, but it will give you the remainder. Okay, Jacob, what's 3 cubed?
27.
Yep, 27. And Brad, how about 3 squared times 2? 18. Denver, what's 27 minus 18?
Nine.
Yep, 9. And then plus 3 gives me 12. And 12 minus 5 gives me 7. Okay, so I get a remainder of 7 when I divide f of x by h of x. Okay, what that tells me is x minus 3 is not a factor of the numerator. Okay, it didn't go in without remainder, and I don't even have to waste time finding the quotient to figure that out. All right, the next one we're going to do f of x. But this time I want to divide by g of x. Okay, so same numerator. Okay, but different denominator, x plus 1. Okay, I can still use the trick here, but does anyone know what I got to be careful about?
The x plus 1.
Yeah, what about the x plus 1? What did I say it had to be?
Negative.
It had to be x minus something. So how could you think of this as a number after the minus sign? Nick?
Negative 1.
Yep. Okay, that's the only thing you have to be careful of. Now that is the number you're using to find the remainder. Okay, if you use plus 1, it doesn't work. Okay, so whenever you see a plus, think of rewriting it like this and take the number after the minus sign.
So it only really works if the numerator has x plus or minus a number.
It's the only time it works. Yep. Yeah, if you've got something, if you had like this, yeah, you can't use this trick. Yeah, it only works if it's a very, very simple denominator. So plug negative 1 into the top. And see what we get. So negative 1 cubed. Negative 1 squared is 1 times 2 is negative 2. Negative 1 minus 2 is negative 3. And then we get negative 4 minus 5, which is negative 9. Okay, double check my arithmetic, but I think we're good. Okay, so again, we divided it out, didn't get a remainder of 0, so that is also not a factor. Okay, any questions on that one? Okay, what's nice is when we divide by something this simple, there is actually a fast way to find the quotient, okay, without doing the long division I taught you today. I won't show you that until tomorrow. Okay, but if you want to divide by something very, very simple, like x plus or minus a number, there's a better way to do the quotient than what I taught you today. All right, so so the next thing we're going to look at is what's called the factor theorem, which is basically the remainder theorem, just when you get a remainder of 0. So I promise you this time we are going to get our first problem when we actually get a remainder of 0. At least I think it's our first one. Okay, so it says you have a polynomial. Okay, we'll call it f of x. The only way that x minus c is going to be a factor is if this number that you plug in is a root or a 0. Okay, because remember, we said earlier, if you can take the number after the minus sign, if you can plug it into the function and you get 0, that means the remainder is 0, which would then prove it went into it evenly without a remainder, so it's a factor. Okay, so when you think factor theorem, basically just think remainder theorem, and I'm hoping I get 0. That's all that it really is. Okay, so I'm going to use the factor theorem to show that x plus 2 actually divides nicely into what I've written below it. So think of this as like h of x. Okay, it's kind of what we did in the previous problem. Let this be f of x. And we're going to divide. So x cubed is 5x squared plus 5x minus 2. And you can divide by x plus 2. Okay, so somebody tell me, how am I going to find the remainder without doing this all out? Okay, I don't want to do the long division. Just tell me how to get the remainder. Yeah.
Plug in the negative 2.
Sure. We're going to plug negative 2 into which function here? The bottom one or the top one?
F of x.
Yeah, f of x, the top one. Okay, and what are we hoping to get a remainder of, Nick, in order to prove that this is a factor?
0.
Yeah, we're hoping it goes in evenly. Okay? So negative 2 cubed plus 5 times negative 2 squared. 5 times negative 2 minus 2. Bria, what's negative 2 cubed?
8. No, 16. No, what? Oh,
Negative 8, yeah. Hannah, how about negative 2 squared? 4, and then times 5? 20, and that's going to be minus 10 minus 2. Okay, negative 8 plus 20, that's going to give me 12 minus 10 minus 2. Okay, 12 minus 10 gives me 2. And lastly, 2 minus 2 gives me 0. So, if I were to do out the long division, you would get a remainder of 0, which proves this is a factor of this. Okay, what's the other factor? At this point, I don't know. It would be the quotient, okay, when I did out the long division. Okay, so x plus 2 times the quotient, whatever it is, if I did it out, that's the other factor. Okay, any questions on that one? Okay, so that's all you have to do if they ask you to prove something is a factor. Okay, just find the remainder. All right, so we've been saying a lot of different things about if something is a root, if something's a factor, okay, all that stuff. I'm just going to summarize everything in this list and show you that they're all the same. Okay, so suppose you have a number that is a solution to the equation f of x equals 0. Okay, that means you have found a number that when you plug it into your function, it comes out to 0. Okay. what would be the solution to this equation? 0 equals x plus 3. -3. Okay, so as I go through these, I'll use that as my example. -3 is a solution to that equation. That also means that -3 is a 0 of that function. It's the same thing. It's also the same thing as saying -3 is a root of the function. Okay, all these things mean the same thing. And the next one here, this one's probably the most important. Basically says that if you know something that's a root, x minus that is a factor. Okay, so if you know something is a root, x minus that is a factor. Or x minus your root. And the reason that one's important is because that's going to help us to do the next problem, which is I'm going to give you 3 numbers that I want as roots. And you're going to have to tell me what the problem would be. Okay? But if we know these 3 numbers are roots, we can very easily figure out the factors. Okay? As long as they give us the roots. Okay, and the last thing, you can also say that if you know a root, that's where it crosses the x-axis, if you were to graph it. Okay, so in the case I have here, if you graph y equals x plus 3, it would cross the x-axis at -3. All right, so let's see if we can figure out a polynomial of degree 3. Okay, degree 3 means when you factor it, you've got 3 sets of parentheses. And I want -2, 1, and 3 to be the roots. All right, so let me start with -2. Okay, if -2 is a root, then what would have to be a factor? -2 is a root, what would be a factor, Ian?
X plus 3.
Yeah, x plus 2. Very good. Okay. If you know a root, x minus your root is always a factor. Okay. What about if 1 is a root? What would be a factor? Tell me something I could write right here, and if you plug in 1, it would come out to 0.
X minus -1. Or just 1.
Just x minus 1, because if you plug in 1, 1 minus 1 is 0. And how about if 3 is a root? What would have to be a factor? X minus 3. Because if you plug in 3, 3 minus 3 is 0. All right, so what I can do is, if they don't say to do anything, you can leave the answer just like that. That's factored. Or you can quickly FOIL this out. It's x squared minus x plus 2 minus 2. And then we could FOIL it times the last one. I would never have you FOIL something out that was more than 3, because it starts to get a little time consuming. But 3 is not too bad. So we've got x cubed, x squared, minus 2x, minus 3x squared, minus 3x, plus 6. Okay, now just combine your like terms, and that's your answer. So x cubed plus x squared minus 3x squared That's a minus 2x squared. What's negative 2x minus 3x? Yep, negative 5x plus 6. Okay, let's graph that. And if we did everything correct, it should cross the x-axis at negative 2, 1, and 3. If it doesn't, then we did something wrong. Okay, so we got x cubed minus 2x squared minus 5x plus 6. Okay, and looks good. Okay, so any questions on how we did that? Okay, taking this and working backwards to get the factors, that's a little harder, but if you're given the factors, it's not too hard to find that. All right, so the last two are just going to be the opposite of what we just did. Okay, I'm going to ask you to tell me the roots. Okay, I'm going to give you the problem, and I want you to find the roots. Okay, so remember the goal, anytime you want to find roots, is you have to try to factor. Okay, if it's a quadratic, you do have another option if factoring doesn't work. What can you always use to solve a quadratic? You could always use the quadratic formula to solve. Okay, unfortunately for a cubic, we don't know the cubic formula, so this has to factor somehow, or you can't solve it. Okay, so they ask us to do what's called factor by grouping. Okay, that means take the first two terms and factor out what they have in common. Okay. What do x cubed and 2x squared both have in common? Yep, an x squared. And John, what does that leave me with if I factor out x squared?
X plus 2.
Yep, x plus 2. Now, the goal with factor by grouping is I'm going to hope I get another x plus 2 over here. Okay, if I factor out what the last two have in common. That's how factor by grouping works. Okay, what do the last two terms have in common?
-4.
What did you say, Luke? Negative what?
4.
Yep, negative 4. And if I factor out a negative 4 from a negative 4x,
X.
left with an x, and negative 4 times what is negative 8?
2.
Positive 2. All right. So now I look at what these both have in common. X plus 2, x plus 2. Now I'm going to factor out an x plus 2 from the first one. And if I factor out x plus 2 from the first one, what does that leave me with?
X squared.
Just an x squared. And if I factor out x plus 2 from the second one, just a negative 4. And you can check it, distribute it back out. X plus 2 times x squared, and x plus 2 times negative 4. Okay, that's factor by grouping. Now, what do you do with each factor to find the answers? Set them equal to 0. Okay, x plus 2 equals 0. X squared minus 4 equals 0. Okay, what's the answer to the first one? Negative 2. And how do we solve x squared equals 4? What do you have to do? Take the square root of both sides. So what's the square root of 4?
2.
2. And? Negative 2. Okay, so notice the highest exponent. Okay, it's a 3. How many answers did we get? We got 3 answers. One of them is a repeat. That's okay. But we still did get 3 answers. Okay, so how many times is this graph going to cross the x-axis? 2. Only 2. Okay, it's going to cross the x-axis at negative 2 and positive 2. Let me show you what happens when you graph something with what's called a root that's repeated. Can somebody give me that problem? Was it x cubed
Plus
2x.
plus 2x squared?
Yeah. Minus 4.
minus 4x minus
8.
8. All right. So it's going to hit the x-axis at 2 and negative 2, but one of them is a repeated root. Usually what happens when you have a repeated root is your graph comes up, kind of touches it, and bounces away from it. Okay? That's what a repeated root looks like. Okay. So some people think, well, is that really only 2 answers? No, it's 2 distinct answers, but there are 3. One is a repeat. Okay, and the last one we'll do, this one it just says use your graphing calculator to find the roots. So how many roots, or how many answers is this problem definitely going to have? Right, it's going to have 3 answers. Now, what we haven't really gotten into yet, and we're not going to until Thursday, is the answers can be real numbers, or they can also be, what kind of numbers are not real? Imaginaries. All right? So we don't know. Okay, we could have reals and imaginaries, or it could be like the last problem where we get 3 real answers and one's a repeat. Well, let's graph it and see what we get. Okay, and it takes a little bit of practice to get used to what you're looking for in a graph to tell, like, are these real answers? Are they imaginary answers? Is it a repeated answer? But I'm going to show you the kinds of things to look for. That's x minus 2. Okay, so this one, okay, looks like it only crosses the x-axis 1 time. So there's definitely 1 real answer. Now, the only question is it repeated 3 times? Is it the same real answer? Or is it 1 real answer and 2 imaginary answers? Okay? The way I can tell is I'm looking at this term. Okay? Because the graph has a local max and a local min, that tells me that there are imaginary answers. This is not the same real answer repeated 3 times. Okay? I'll show you what a real answer repeated 3 times looks like. Okay, and I just took a guess it was at 2, and I was right. Okay, if I wasn't, does anybody remember how you calculate the root? Luke?
Second calc.
Yep.
Then you go to 0.
Then you go to 0. Exactly. Okay, in this case, I don't need to. That is the only root. Okay, here's what a graph would look like if you had the same real root repeated 3 times. Let's graph x plus 3 times x plus 3 times x plus 3. Okay, where is that going to cross the x-axis?
-3.
At -3. And it's going to be a triple root. Okay, so what happens at a triple root is it kind of flattens out in the middle. It never really takes this turn up, back down, and back up. Okay, it's always going up, maybe slightly flat, and then continuing up. Okay, that's what a triple root looks like. Okay, so that's the difference in how you look at those. Blue one, that's 1 real and 2 imaginary. Red one, all real. It's a triple root. Okay, and the double root you guys saw in the last one. Okay, so any questions on that? All right, so that pretty much wraps up what we're going to do with long division. Tomorrow I'll show you a faster way to do long division, but it only works for very simple problems. So you still need to use what I taught you today for complex problems, but simpler problems, there's a faster way to do it. All right, so homework tonight. You could just simplify this and say 9 through 21 odd. Okay, so it's 1, 2, 4 through 6. And you know what? Just do 9 through 19 odd. Okay, 9 through 19 odd. And then 25, 27, and 32. So we'll take a look at that. We'll go over it tomorrow. Just a reminder, I will be here for extra help on Thursday, in case anybody wants to stop by before the test.